Dear civil engineering viewers, welcome to Gani's method, rotation contribution method. So I'm Dr. Ramesh Babu from Galgotias University. Now here we go. So Gani's method was developed for a building frame by Dr. Gasper Kani, a German, in 1947. This method employs slope deflection equations in iterative procedure. It falls under the category of stiffness method. We require the degrees of freedom. In Gani's method, the entire joint moment is taken for iterative correction. We take the entire joint moment. Okay. So, for example, if a joint is connected by four members, we take all the four members into consideration and calculate the entire joint moment. The iterative process gets completed when the student finds two successive values of moments nearly equal. Now you consider this frame. If this frame is subjected to loading, this frame will have a deflected shape just like this. So here what do we do is we neglect the vertical displacement of the joints. We consider only the rotations and horizontal displacement at any level. For example, horizontal displacement of del E, del F, del G and del H. Okay. And if you take the rotation, if this is the L member, so you can calculate that the rotation at L will be the LM, LG, LK and LB. So here it is given the theta L is the rotation of LK, LM, LB and LF at the point or at the joint L. So how to find out the net support moment? What is the net support moment for any member? For example, if you take any member that is LM, what is the net support moment? So you have a moment here and you have a moment here. This is said to be the final moment or next support moment. So it is divided into three parts. This is the first part, which is said to be the fixed end moment, and the second part is the moment due to rotation contribution due to the near end. So near end means due to L. So you can see that this is fixed end moment FEM, and the second one is MIJ dash, and the third one is moment due to rotation of the fore end, that is M. So it will be M dash JI. Also you can call it as M dash ML, and this moment is called as M dash LM. This is rotation contribution moment due to near end, and this is the rotation contribution moment due to fore end. So in Gani's method, you have to note down three things: that first you need to calculate the fixed end moment, then you have to calculate the moment due to rotation contribution of the near end, and moment due to the rotation of at the fore end. So these three are the moments which we would like to calculate, and based upon this we will be evaluating the final moments, that is nothing but M LM, as well as we will evaluate M ML. So this is how we do now. Now we will recall the slope deflection equation here. You can see that the final moment is, as I told you, this is the first part, that is fixed end moment. This is the second part, moment due to rotation contribution of the near end, and this is the third part, moment due to rotation contribution of the fore end. So near end is L and fore end is M. So MLM equal to fixed end moment at L plus 4 EI by L into theta L plus 2 EI by L into theta M plus 6 EI delta by L square. Now theta L and theta M are nothing but rotations of LM. For example, you can have LM like this. So this is the theta value of L, and this is the theta value of M. Okay. Now what we do is we will take 2 EI by L into theta L as M dash LM and 2 EI by L into theta M as M dash ML. So if you substitute it in this equation 1, you will get finally M LM equal to fixed end moment at L plus 2 into M dash LM plus M dash ML. So this is generalized and written here as M dash IJ equal to MFIJ plus 2 M dash IJ plus M dash JI. Now Now this is again written, that was for only one member LM. If you have so many number of members like this, then you can write down the Mij equal to summation of all fixed end moments meeting at the particular joint plus 2 into M dash Ij is summation of all rotation contribution factor of the near end. So this will be I, this will be J, this will be J2, this will be J1, this will be J3, and this will be J4. So these ends are the farther end and this I is the near end. So you can see that this is more generalized equation for the whole problem. So from this you can get this M dash Ij equal to, so we concentrate on the rotation contribution of the near end. So that is equal to minus 1 by 2 times summation of Fij plus summation of M dash Ji. This is fixed end moment part 1. And this one is part 3. And what you have on the left side is nothing but part 2, as I explained in the earlier slides. So in the above equation, we don't know what is theta L, we don't know what is theta M. So we do not know the values of M dash Ij, or we do not know the values of M dash Ji. So what we do is, we assume this second part and third part to be 0. Then we will calculate the value of M dash Ij for every joint that rotates. So first we will assume 0 for the farther end as well as for the near end. Then using iterative cycles, we will improve the values of M dash Ij, and we will continue the iteration cycle after cycle until we get two successive values of Mij as equal. So let's see the procedure here. Now the important thing is rotation factor, which is nothing but U equal to minus 0.5 into distribution factor. So this is the scheme of Kani's method. At the center you have summation of all fixed end moments. For example, this is the joint B, this is the joint A, this is joint C. At the center you have to add fixed end moment of BC plus fixed end moment of BA. So this is added and written at this location. Then here you have rotation contribution factor UBA and UBC. Okay, so this is fixed end moment and this is fixed end moment. This is the Kani scheme. Now inside cell you have to enter the total fixed end moment, summation of all fixed end moments. Now we will solve a simple problem. So look at this problem. You have here UDL at the span AB, and at the span BC you have point load, at the span CD you have point load. Then we will find out the fixed end moments as usual. So here you have 10 kilonewton per meter. So for this you will get minus WL square as M of AB, and M of BA is WL square by 12. So then you calculate M of BC, M of CB, M of CD, and M of DC. Once you are end up with the calculations, then you calculate the rotation factors. So similar to moment distribution method, here we calculate the relative stiffness as I by L for BA, BC, for CB and CD. Then you add the sum of sum of the stiffness is obtained here as 7I by 10, and for this also you obtain 7I by 10. Then you calculate the distribution factor similar to the moment distribution method, that is I by 5 divided by 7I by 10. Then here it is I by 2 divided by 7I by 10. Then this is I by 2 by 7I by 10. This is I by 5 by 7I by 10. You get all these values. Once you get all these value, you multiply this by minus 0.5 to obtain the rotation factor for Kani's method. So these are the values obtained, as you see, by multiplying these factors by minus 0.5. So once you are done, this job is over. Then you proceed further, where joints A and D are fixed. Hence there are only two joints, that is B and C, at which the iterations to be carried. Here you note down that at joint A there is no rotation. Theta is 0. And here also theta is equal to 0. So no rotation at these points. You have to nullify the moments at B and C, as you see in the moment distribution method. Now, first of all, we have to calculate the summation of fixed moments. So this is summation of M ij. So that is nothing but MFBA plus MFBC. These are the fixed moments calculated in the previous step. So you have calculated MFBA and also MFBC. So this is MFBA and this is MFBC. Now you add these two and substitute it here. Similarly, at this location, this is MFCB. So as you see, MFCB is 14.06 and MFCD is minus 25. Then you are getting these two values. And here you have to enter the rotation contribution values for UBA. This is for UBC. This is for UCB. This is for UCD. Like this you got to enter. Then now we will proceed how to do the iteration. So this is the pictorial representation of all the fixed moments. Here you can see that this is the fixed moment MAB, that is MFAB. Okay. For example, I'm telling you this is MFAB and this is MFBA, this is MFBC, this is MFCB, this is MFCD, this is MFDC. Now you have added and entered in the cell respectively. Now how to carry out the iteration? Let's see how to carry out that. First you assume that this M dash, first let us take the point B. Okay, this is the point B and this is C and this is A. Okay, so you want to calculate the moment at point B. So in this case, what do we do is, this is further end, C is further end and A is further end. So we assume theta C is 0. Okay. Now M dash CB. So M dash CB is the further end. So this is M dash AB. Okay. So we assume M dash AB further end as 0 and M dash CB further end as 0. Okay. Then you will get the value of M dash BC. So that is what written in the first step. Okay. Now what do we do is, we will take the joint C. So we will take the joint C here. This is D and this is B. Already I have calculated M dash BC. So here the new M dash BC will have some acceptable value. Okay. Now this M dash BC is used in the calculation of M dash CB and M dash CB. Okay, you understand? Now, first we calculated M dash BC by using the farther end M dash CB to be 0 and M dash AB to be 0. Then we calculated this M dash BC. Then this M dash BC is taken at this location and it will be used for calculating M dash CB and M dash CD. So this and this is the first iteration. Okay. Now what do we do is, now you have obtained M dash CB. Okay, so this is the iteration 1, this is iteration 1. Now through the iteration 1 you have obtained new value for M dash CB. That new value for M dash CB is taken at this location, M dash. Now what will you do? You will calculate M dash BC by using this M dash CB and M dash AB. M dash AB is already 0, forever it is 0. Okay, now you will get new value of M dash BC. This new value is utilized for calculation by substituting in this location. So using this, you will get another value of m dash cb. Then you take this m dash cb and substitute it here. Then you will get m dash bc. So this cycle is repeated again and again. So if you want to know how to perform this, let us solve a simple example and it will be very easy for you to catch up. Now in this example, you can see that first the fixed end moment is 16.14 kilonewton meter and summation of fixed end moment. Here the summation of fixed end moment is minus 10.94. Now rotation contribution factor is minus 0.143 for B dash A, and for BC it is minus 0.357. So for CB it is minus 0.357. For CD it is minus 0.143. Now the formulation is UBA into summation of fixed end moment plus m dash AB plus m dash CB. So similarly here UBC. Now these terms are the same terms are used in this column and this column. Only difference is you have to multiply by UBA and UBC. Now let's take the value of m dash CB. You can see that it is UCB into MFC plus m dash BC plus m dash DC, and here it is UCD into MFC plus m dash BC plus m dash DC. Now I will explain you simply. Now again you take this joint B and here it is C and here it is A. Now for example, here you have MFB, summation of MFB. Okay. Now this is further end. This is m dash CB. This is further end. You have m dash AB. Now this is what I have written here. You understand? Now similarly for each and every joint you have to write. Now suppose you want m dash BC. So how will you calculate m dash BC? For m dash BC, suppose you take this as C and this is B and this is B. Now here you have to calculate MF C. Now here you have MF DC further end, and here you have M dash BC. Now you can verify the formula here. It is equal to MF C plus m dash BC plus m dash DC. You have the same formula for m dash CB as well as m dash CD. So for m dash CD, that is m dash CD and m dash CB. For these two, you have this same formula. So can you recognize this expression? UCD into MFC plus m dash BC plus m dash DC. I have explained here. This is MFC that is written here. Then here this is further end m dash BC that is written here, and this is m dash DC that is written here. Okay, so don't get confused with the calculations. Actually, the student has to listen keenly so that he will be able to understand. For example, if you want to calculate for m dash BC and m dash BA, so you have to draw this line. In this line at the center you calculate the summation of fixed end moment, which is written here at this location 16.14. then this is farther end, so m dash CB, and this is farther end, so farther end is A, farther end is C. So you have m dash AB and you have m dash CB. Once you understand this formula, the next step is you can substitute here m dash AB as 0 and you can substitute m dash DC as 0. Then you are going to add only these two terms that is being written here, MFB plus m dash CB, and here also you have FC plus m dash BC. So you can see that MFC plus m dash bc. So this term you can see here, and also the same term is substituted here, and the rotation factor is only different for these cases. Okay, so once you understand this, you substitute the value of the rotation factor here. For example, here you have rotation factor minus 0.143 into fixed end moment is 16.14, and first of all we assume this as 0. So you can see 0 here. Then from this you will get minus 2.31. Use the same formula except that UBC is there, so you get minus 5.7C. Now you have got a new value for m dash CB, which is 5.76. Okay. Now this value is being taken for this iteration. So once you substitute it in this iteration, for example, 5.76 is carried over to the next iteration cycle of C. So here UCB into fixed end moment plus m dash BC. So this m dash CB is taken to be for m dash BC. Then you get 5.96. Then here also that for calculating the m dash CD, so m dash CB and m dash CD, you are going to use this value. So once you use this value, finally you are getting m dash CB. So what is the value obtained for m dash CB? That is nothing but m dash CB equal to, I will clarify it once again, m dash CB is nothing but 5.96. So once you take this 5.96 that is being calculated from here, that is again substituted in these two expressions. Then from these two expressions you are getting this m dash BC equal to minus 7.89. That is being used for calculating these two expressions. So you end up with the new m dash CB. So this is carried over to iteration for these two columns. Then you get this red color m dash BC, which is being substituted for this m dash BC expression. So here you substitute, then you find out new value of m dash CB. So this minus 8.6 is for these two columns. Then 6.82 is that you substitute 6.82 for these two columns. You get minus 8.2. You get again 6.83. Now we can stop. Why I stop at the fourth iteration is you can see that the consecutive values 3.27 is almost equal to minus 3.28, minus 8.16, minus 8.20, 6.82, 6.83, 2.74, 2.74. Now I hope you have understood the iterative procedure. Now we can stop here, and these are the final values of m dash BA, m dash BC, m dash CB and m dash CD. So once you get these values, you go ahead and substitute the values for finding the final moments of MAB, MBA, MBC. So you can see that it is similar to slope deflection equation, m of AB plus 2 m dash AB plus m dash BA. Now already we assumed m dash AB and m dash dB to be 0. Rest all the values of the final step are substituted in these expressions and the final moments are obtained. So here you can see the cycle moments are represented. Directly you can understand these moments. So first it was assumed 0 and you got 5.76. This 5.76 is used for calculating these two values. Then this 5.96 is used to calculate these two values. Then this 7.89 is used to calculate these two values, and this 6.72 is used to calculate these two values, and 8.16 is used to calculate these two values, and this 6.82 is used to calculate these two values, and 8.2 is used to calculate these two values, and 6.83 is used to calculate these two values, and this 8.2 is used to calculate the values. So actually The author has done 5 cycles, but I stopped with the 4th cycle because that consecutively we are getting the same values. So let me stop here. And these are the final moments: minus 24.11, 14.27, minus 14.26, 19.52, minus 19.52, 27.24 kilonewton. These are the final moments. Now once you are done with the final moment, these are the bending moment diagrams as represented here. You can see that the simply supported moment is WL square by 8, and for BC it is WAB by L, and for CD is WL by 4. Then you superimpose these moments where you get the final moment values for these locations, and these are drawn in this fashion, and you have to superimpose the simply supported moments, and finally you get this bending moment diagram. So this bending moment diagram is drawn on the tension side as represented here. Thanks a lot for watching. If you have any doubts, you mention in the comment section.